So, okay, we're set. So we are going to continue the solution for this problem. And before we go on, let's answer the question that Hassan asked last class. So just see what I'm going to do over here. I'll assume that this is the roller over here, and this is somehow the gear. So the force indicate that the other gear is pushing in this direction, and therefore we will assume that this is going to rotate in this plane. Now what happens is that I unintentionally somehow, I don't know why, is it just like me, or I assume that the material is coming from here and getting out from here, but it's actually not. The material will be will come here, like with this, for example, thickness, and then it will be squeezed from the other end like that. Now, there is no doubt that we all agree, there is no disagreement about the fact that the distribution down on the roller is going to be upward, because you're squeezing the material down so it will react upward. Now, what is the direction of the force generated by the material as it is being squeezed on the roller? Just think about it. It is supposed to be this way. Why? How do you sense this? Well, very simple. Assume that you are manually trying to squeeze the material. Someone would expect that if the material is here and this is the surface, and let's assume the roller is here, okay? And now what you want is to squeeze the material to come right there. Now, if the material is too hard, you know, to be rolled, or if you are not strong enough, somebody would expect that you will try to rotate this in the direction where similar to the gear, and when you push, if the material is too hard and you let go, it will reverse. Why? Because indeed the material is opposing your action, and logically that if you try to push this way and something is pushing on the other way, it will go in the other way, and that's how the torque is balanced. One of them is pushing on a clockwise, the other one, Masleh, you want to say something? And the other one is pushing in a counterclockwise. I can't hear you, Masleh.
Isn't like friction?
More or less, yeah. Yeah, you can think of it this way. The volume as it is, oh no, I don't need to add one more slide. As the volume is being crushed over here, you can imagine that there is a force is going to be generated on the other direction, trying not to push it that way. So that's it. Now, so let's get back to the problem. I hope this explains why the torque over here is being generated by the reaction, which is this one, which is trying to oppose the motion of the plate. Okay, so this is the reaction of the material on the roller. The roller is trying to push here, but the material is trying to push in the other direction. Similar to the roller trying to push down, but the material is pushing up. The roller trying to push forward, the material is trying to push backward, and that's how the whole thing is balanced. So if you recall, I'm going to do this very quickly. This one is the distribution, 4.2 Newton millimeter, and this one is this distance. You see that? That's the distance. Sorry, this is not the distance I'm talking about. The distance I'm talking about is here. over here. So Shabab, before, so I don't need to go back and forth, I mean. So I want you to remember, look, the roller here is 200. If you want to go to the location of the bearings, you need to add 45 to the left bearing. If for any reason you want the distance from bearing A all the way to the other bearing O, then you need to add 45, 45, and 200. That's 290. If for any reason you need to include the force in the gear all the way to point O, which we will do when we take the moment, then you should add 45, 45, 270. That distance 70 is the distance from the location of the. So in the free body diagram over here, we have the 70 and we have the 290. The 290 is coming from the what is it? The 45, 45, and the 200. So it is 290. So this is 200. So this is in millimeter. This is the other distribution in the y direction. So we got these two forces. I remember I explained this very well last time. Then we said that the torque is can be calculated as this force is being multiplied. Okay, this force PZ is being multiplied by the 50. So what we will have the torque being determined. Then we can say that the torque generated by the gear, which is F cosine 20 multiplied by the radius of the gear, which is 76 divided by 2, it's 38, is this one is positive. Why? It is acting in the positive x-axis, while this torque is acting in the negative x-axis. That's why we have negative, positive, which is equals to 0. Okay, from that we got the force, and now our job is only to use the equilibrium equation, summation of moment, summation of force, in order to compute the reaction, to find the reaction. So we start first with the Z direction. So we will sum up the moment along the Z. This is mz at point O. What are the forces? In red, this one, py, ra along the y, and of course the radial direction force coming from the gear. Good. We know their distances. This one is located at a distance of what? 200 divided by 2. That's the roller is 200. We divide by 2 because it's acting in the middle of it. That's 100. And then plus 45. So that's why we have 145 multiplied by py. And then this one is simple. This one is located at 290, and the other one is located at 290. Did I move? Yeah. So this one is located 290. The other one is 70 plus 290. And in that case, we have this one, of course, in the opposite direction is minus 360 multiplied by the force, multiplied by F cosine 20. The radial component is cosine, the tangential component, which causes the torque, is tangent, is cosine, I mean. So this one is a sine. Clearly, ya shabab, we have only one unknown, which is the reaction along the y direction in the bearing A over here. So we find that reaction and we get it minus 25.6 Newton. Then we go to the next step, which is getting the moment along the y direction. So I'm gonna mark this with a blue. This is the y direction. And now we want to sum up the moment along the y. So what are the forces that causes moment along the y? This one, our friend, which came from the, pushing the material forward. This one is the radial for the Z reaction on bearing A, and of course the tangential force on the gear. Remember, we know these distances, all of them. هذا 145, this one 290, and this distance, all of it is 360. You will see them here. Again, look at them. 45, 290, 360. Just watch out for the unit. Don't forget, this is all, the direction is not written. Is not written summation of the moment clockwise, counterclockwise. Why? Because we assume here that the moment, which I should make it maybe clear for you, the moment which is rotate such that your thumb is pointing toward the positive y is positive. Any other one pointing downward is going to cause a negative. That's why all of them are negative. Okay, so what do we get? We get RA along the Z direction. Now we have two forces, okay, at A. We know what is RA Y, and we know what is RA Z. Now, what do we do? All what we need to do is to find the resultant. Now, the resultant is here, which is the square root of RAY square plus RAYZ square. And what do we get? We get this one, 1,792. That's it. I don't care what is this angle. Bearing is a circle. You push it from any other direction, it doesn't matter. What I need is the magnitude, the maximum, not RA along the Y or RA along the Z. This is just for us to make the calculation. The true force is this one. Okay? Now, what do we need to do? Interestingly, ya shabab, you will see that for bearing O, all what you need to do is to sum up the forces along the Y direction, along the Z direction. And there you will be able to determine RO along the Z, RO along the Y. And by doing so, you will be able to find the resultant just similar to RA. And there you have it. This is the resultant. It is 640.6 Newton. Now, in the question, it says that we should use identical bearings, similar bearings, okay? If the question does not say that explicitly, then you should still use same bearings. So you don't use different bearings unless otherwise stated, okay? And so have two bearings. One of them has a resultant force of 640. The other one is 1,970. So clearly, we are going to use the location A as the critical one. And so reaction at A governs. Yeah? We have to use the reaction at A. Now, if you recall, we said that the combined reliability should be 0.92. And that means that the goal, the reliability that you should target is supposed to be the square root of the combined, the multiplication of both. So the square root of 0.92 will give you 0.96. Now look, ya shabab. What do we have here is a bearing. I just try to pull the equation. So if you go back to the question, we have a bearing, okay, with a rated FD. That's number one. We have been told to use AF, which is 1.2. We have been told to have L desire as 30,000 hours. Look at it. It's 30,000. We have been told that ND should be 300 RBM. And we have been told to use a reliability as a target, desired reliability, okay, as 0.96. Well, now, this is a complete party over here. Why? Because everything is different than the catalog value. So should we get crazy? No, of course not. We spend the whole week trying to make up an equation that just do that. So what are we going to do? We are going to use this equation, C10. So actually, it paid off in the end. C10, the catalog value that I should look for, is equal to AF multiplied by FD multiplied by XD divided by what? X0 plus theta minus X0 multiplied by ln 1 over RD to the power 1 over B, and everything is to the power 1 over A. I can't remember. Oh, I memorized it. That is very nice. So, what is this? First, this one, and this one are the Weibull distribution value. They are the same. We have only one set that was reported in the book. We'll keep using it again and again until otherwise stated. Okay? Then, what is A? This is a ball bearing, so it is a 3. What is AF? It is 1.2 given by the problem. And what is FD? It's what we found. It is the reaction, the resultant at A, which is 1,792. So what is RD? It is 0.96. Remember, the catalog gives you 90%. This is 96. Okay? And then we have XD. What is XD? XD, ya shabab, if you recall, okay, XD is equal to L desired divided by L rating. The rated value of the catalog. Now, we know that the rated value of the catalog is 10 to the power 6. 1 million what? Revolution. Now, what do we have? We have LD, ND, both of them, and we multiplied by 60 to make the conversion. Now, LD is given to us 30,000 hours. ND is a 300 revolution. Okay, now look at the beauty here. We do not need to care what were the rated hours, and rated speed. We used the rated revolutions, and that's it. All what I need to do is to convert my need, which is 30,000 hours and 300 RPM, into desired revolutions. Those are the revolutions I want. And for that reason, look, it is 30,000 multiplied by 300 multiplied by 60, and then divided by 1 million. And there I got XD. And that's it. What did I get? Ya shabab, I got this one. 21.59 kilonewton. Now, what does this mean? Just be patient with me. I need to take you back all the way to slide something. Patience, ya shabab. That's too much. Over here. Now, I have to admit, in the book, in the solution, it says, first of all, it says, I want series number 2. So we should be in here. That's series number 2. not series number 3. Another thing, we got a C10 of 21 point something. Now, if you look here, that's a C10 of 16, and then that's a C10 of 22.4. In the solution, this value was picked. It says a 35, okay? In the solution, let me exactly bring it up, exactly like what is written, says a 02-35 bearing will do. I honestly don't see why is that. I have to admit, maybe I am missing something over here, and I will try to check it out. But we applied the factor, the application factor. And to me, when you apply the application factor, you gave yourself some factor of safety, and you should use the nearest one. And the nearest highest one is this one. But the book decided to use the second one. I think it's because it was too close. Okay? However,
What's
yes,
the 02 for?
what is that?
02. What's the 02 for? The
0.
It says 02-35, right?
Yes.
So what's 02?
02 is series 2.
Oh, okay.
03 is series 3. And then we picked 35. These are distinct. Okay. So let's assume that the book here assumed that 21.59 is too close to 22. Let me use the next one. That's it. Okay. And I can see that. I can see it's okay. Now, what's important here, what is interesting is how much now you guys evolved from 307 to 308. When we design shaft, like the one we have now, all what we did is to draw a free body diagram. And then we put forces and moment and torques, and there is no measure. There's no measure. There's no size. In the past 307, we told you, you can start from the bearing. Bearing will be subjected to torque. Bearing location will be subjected to torque. There is no bending. And you can use yielding as a first approximation. Now, when you do the reactions, when you find the reactions, what you need to do actually is to find the proper bearing. And when you find the proper bearing, as a first approximation, in here, you would say, oh, the diameter is supposed to be, this is the bore size. The bore size is where the bearing is going to be mounted. So you cannot just use yielding, or because that won't fit. If yielding told you you should use 20, you're not going to use a 20 because a bearing with that bore size may fail. Okay, so what are you going to use? You're going to use a bearing which needs 35. So you will have to use 35. So this is a more realistic way to estimate the beginning of the diameter. And then you move to the next one, you move to the other one. Do you understand? You have to pick a bearing from the market. So deciding about the bearing size from the beginning, using just only the reaction forces and so on, is very, very interesting. Okay. So, yes?
Yes, in the previous question, from where did you get the Weibull parameters?
These are the same Weibull parameters that we have been using. Let me show them to you. When we started talking about the distribution over there, when we first had the Weibull distribution, okay, we've been using these values, and they will be used again and again and again, unless, as I told you, some other values are presented. These are supposed to come from the catalog. Okay, we're assuming here that we're using a ball bearing, so the catalog value for those bearings are the same. Okay.
Okay, thank you.
Okay.
If we have a thrust,
Yes.
we should calculate FE instead of FD. Is that right?
Yes. 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 That's right. That's right. So let's move on to yes.
What about the reliability? How did we get the 0.96?
How to get?
How did we get the 0.96 reliability in the previous example?
Oh yeah. We said in the question here that we need a combined reliability of at least 0.96. Something wrong happened to my PowerPoint, and when I made a PDF version of the slides, of course I am updating the slide every day. So inshallah next week when we finish chapter 11, I will update the final slides to you. But what did we say? We said that the reliability, okay, for two bearings located at position A and B is the multiplication of both under the square root. No, this is not what we said. We said that the reliability, okay, the reliability of the bearings, of two bearings for the shaft is the multiplication of R, B, and A. That's what we said. And then we said, let me just pull, I want to just double check it, something over here. And then what did we say? We said that what happened if you want a targeted reliability? We said that the combined reliability, the goal reliability. So let's say I told you we want a combined reliability of 0.92, like in this problem. It means your goal should be, we said that the goal reliability is supposed to be here, ya shabab. These two equations are not showing up. It's supposed to be equal to the square root, okay, of the goal, of the reliability. Do you understand? So we have been told that we want a combined reliability of 0.92. So then the goal is supposed to be the square root of that, and that's how we got it. Do you understand this?
Yes, that's clear.
Now, remember here you are designing. So you know the combined reliability, you take its square root, and then you look for a bearing which with a square root reliability. Be careful. There is another question. If you have a machine running now, and then you ask the operator, what is the reliability of bearing A? What is the reliability of bearing B? And then he told you, we picked these two from the catalog, and both of them are identical, and they have what? They have the same reliability, RA and RB. Then the reliability of the system is the multiplication of both. That's a different scenario. That's a scenario which is already physical, and you want to know what is the reliability of the turbine. The reliability of the turbine is prone to the failure of one bearing only. You don't need both of them to fail, just one. And we discussed this in the class. If you want, you can return back to the video note, okay? All right, now what do we want to do is to move on to the next topic, which is the tapered roller bearing. Okay, now clearly, ya shabab, that this is tapered. So the bearing is tapered, and there are rollers, and rollers are these. So they are no longer balls, And what happens is we have 4 main components for this bearing. The cone, as you see, this is the cone. Look at it. The cone sits here at the bore where the shaft is going to come. Okay. And then we have 2 cups on the top, housing from the outside the bearing mechanism. We have a tapered rollers, okay, and we have a cage. The cage here is similar to the separator in the ball bearing. Its job is to keep each roller in its place always, and the rollers does not interact with each other. Okay, so if you look at it, this is the cage, ya shabab. Look, the cage is this material over here, this ring, okay, which keeps each cylinder, tapered cylinder alone. In here, we have the cup, right? And inside we have the cone, if I'm not mistaken. Yeah, the cone is inside, the cup is outside. Now, what you need to understand is some details about tapered bearings. The first thing is that they can be used for a situation where only radial load is applied, or where only thrust load is applied, or both combined. However, there is something which is different here. If you have a situation where you have a tapered roller bearing like this installed, and then you applied only radial load, what will happen? Automatically, because of this tapered geometry, the bearing will generate F axial, which is a thrust load, and it will generate F radial. So if you put a bearing by itself, which is not usually the case, then you need to resist that induced thrust load. You need to cancel it out. Because here, you're not applying a thrust, but there is auto-generated. That's why we call it induced. It's like coming within the system. The system is generating that force. So what do we do? Well, it turns out that the best way to do this, to deal with this, is to mount 2 bearings in some sort of opposite way. Okay, so you don't put one bearing like this and then the other bearing exactly the same way. You have to put them in a way which we call, look at it. There are 2 mounting methods. The first one is called with cones back facing each other. So the back and the back facing each other. Or this is called direct mounting. Or the front and the front facing each other. Do you get that? This is the front facing each other, and we call this indirect mounting. It makes a lot of sense, right? If one would generate an induced reaction on this side, I flip the other one and I will induce a reaction on the other side, and they will cancel out. Otherwise, what will happen? That force, thrust force, will try to separate the one ring, one trace from the other. Okay, so if you look in here, what do we have? We have indirect mounting and we have direct mounting. And as you see in here, okay, the two are either back, the cone is back to back, or or they are face to face. So what is also important here? It's always, ya shabab, with tapered bearings, you will always see these lines. You see them? What are these lines? These lines are measured geometrically, theoretically, and they should be provided within the geometry of the bearing. We have two important information in here with respect to geometry. The first one is what we call the effective spread. Spread means how the two bearings are spreading or spread with respect to each other. So if you look, this down here is the effective spread, and we have AG. AG is the geometric spread. What does that mean? It means that from a geometrical point of view, these two bearings, okay, have like some sort of a centroid, and from the centroid to the centroid, I measure how far they are. But the effective spread is what is important. Why? Because actually, ya shabab, the reaction, the induced load, FA, induced, and the FR are going actually to be applied exactly at that point. The point between the axis, the middle axis of the shaft, and this line. Okay? So just to show you, this is, look carefully over here. Look, this is the effective, like there, over here, that point and that point. So when you measure the effective distance, it means this is effectively the distance from the point where the actions of the forces is taking place on the left one to the right one. This is very important. Why? Because now when we draw the free body diagram, we need to know where is this effective spread. And this is where we are going to locate the forces. When we locate the forces in that point, we will know exactly how far is that force from the other bearing. When we take moment, the distance matters, right? So this is why these two are important. Things will come. This is a catalog value. Don't worry about it. I'm just showing it to you. It's not even very clear, but I will talk about it when we have an example. So the question now, what is this induced reaction? What is it? I mean, it's crazy. You told me you put a radial load and then you get a reaction axial. How much is it? Well, we don't need to make any derivation. It was like driven by Timken, the company for bearing, that the induced reaction thrust load by a tapered roller bearing, when it is subjected to a radial load, then the radial load, if you multiply it by 0.47 and divide it by K is a constant kind of, and you multiply it by FR, you will get this, how much this induced thrust. Now the question here, what is K? K is the factor that depends on geometry. And look, very interestingly, for design purpose, it is recommended that K can be first estimated as 1.5 for radial bearings and 0.75 for steep angle bearing. This is very good info. You don't need to maybe memorize it now, but you need to know that this value exists. This is similar to when we taught you how to design shaft in 307, and we told you in chapter 7 that there is a table which gives you a reasonably good engineering assumptions for stress concentration, like KT, KTS, do you remember? The idea is that you as an engineer, you can just say, no, I don't want to use K equals to 1.5. I'm gonna make it 2 or 3 or 1. It's up to you. But how long would it take you to arrive at the correct answer is different. We think we think that these values were tabulated because they are a good first approximation. Understood? Okay. Come back to that K. Don't worry about it. Now, then what are we going to do? Now, we know that there is a thrust. And we know also that tapered bearings are designed to take thrust load. So we are back now to the concept of having a combined thrust loading and a radial load. So what did Timken do? They said, okay, let's use the same equation we have before for Fe equals to V x VR, okay, multiplied by Y multiplied by plus Fy multiplied by Fa. And then they said that for tapered roll bearing, X is recommended to be 0.4, V is recommended to be 1 for all cases, and using K factor for specific bearing for Y. We'll see how are we going to do that, but we will end up with this equation. So we'll have Fe equals to 0.4 Fr plus K Fa. Do you see that? Now, we have to be just very careful right here that Fa in this equation combines, it is the net axial load. Now, the net axial load, you'll see, it's not like before. Here, we have an applied thrust load, and we have an induced thrust. And not only this, because bearings are mounted back to back, face to face, whatever, that induced reaction will be going in the same direction as the applied thrust load or opposite to it. So there will be adding and subtracting. You get that? So also in 307, we told you something when we give you the design project and so on, which is, if you recall, we told you when you have a shaft and it is subjected to a thrust load, you need to assume that which bearing will take the thrust load. That's what we did. We did not say that both bearings will take the thrust load. And we told you just assume any one of them. We did not get you into the details. We didn't care. Why? Is it because we are teaching you something wrong? No. Can anybody tell me why we didn't care a lot about which bearing? So if you have an example over here of a shaft like this, and then there is a bearing here, and then there is a bearing here. And then I told you that which of these bearing you will take Fa, and you said this, and there is an applied Fa. Okay? Why we did not care? Maybe somebody would say, no, Fa is here. So which one? The green or the blue? We didn't care. Can anybody remember why not?
Maybe because
I
of
think critical
the
point.
shoulder.
What?
I think it was based on the critical point.
Because the bearing
Another answer?
Because the bearing allow for a deflection.
Another
Maybe
answer?
there are two shoulders, so both bearing will have the same dimension.
Well, let's cut it short because you have only a few minutes, and then we will wish you a happy weekend. Because we didn't care. The real idea, let's assume we didn't care about axial load. We did not even calculate it. We did not calculate it. We did not include it in the design because it is, we said that normal stress generated by bending is more dangerous than normal stress generated because of compressive load. So we didn't care. But now I want to tell you one thing. If you draw the thrust force diagram, if you assume the blue condition, this is it. So if based on the blue assumption here, if you have a buoyant right there, there is no thrust load. But if you have a buoyant here, the black one, there is a thrust load because it's located right here. Similarly, if you consider the green assumption, then the thrust load will continue all the way and it will end here. So this point, this point, this point, all of them have a thrust force. But we didn't care because the thrust load wasn't considered, wasn't important in the analysis. So whether that point has a thrust or not, we didn't care. But you need to understand that in any other situation, maybe it will. Maybe if not from stress point of view, maybe from deflection or from clearances and so on. We're not going to talk about that. So now we need to know which bearing is actually going to take the load. Which one? I have two bearings. Look at them. And one of them will take the entire thrust while the other is not. The difference here is that we will know which one. In 307, we told you, pick any one. You got that? So our design in 307 is still okay. There's nothing wrong with it. All right. Now, ya shabab, I have to stop and then take your attendance quickly because we don't have time. When I call your name, you can leave right away. This is section 6 and we need section 7. So let's see who's here. يوسف اليوسف.
Yes, sir.
ماجد العباد.
Yes.
حسن.
Yes, here.
عبد الرحمن.
Yes, here.
دعبوس محمد.
Yes, here.
عبد العزيز. عبد العزيز, are you here? أحمد دوسري.
موجود دكتور.
عبد الإله.
موجود.
خالد.
موجود.
مصلح is here. سعود.
موجود سعود.
عبد الله. حجاب. Oh, he's excused the other. سلمان.
موجود.
فارس.
موجود.
طارق.
موجود.
عمر is excused. مصطفى.
موجود يا دكتور.
العمر علي.
موجود دكتور موجود.
خالد العتيبي.
موجود دكتور.
حسام.
موجود يا دكتور.
حسام, are you here?
Yes, here.
Okay. هاشم.
موجود.
and سلطان.
موجود دكتور.
نايف.
موجود دكتور.
محمد is here. عبد الله الزهراني.
Yes.
مصلح.
مشعل الزهراني موجود يا دكتور.
مشعل. جعفر.
موجود.
مؤيد is here. علي.
Yes, موجود.
and Hassan. Yeah, Hassan is here as well. Okay, يا شباب. Thank you so much. Have a nice weekend.
Thank you. You too. Assalamu alaikum.
السلام عليكم.